In this video, we talk about how kernels are broken down into blocks and how these blocks are launched on compute unit. So let's look at what we have from the previous video. We have asynchronous compute engine and assuming this asynchronous compute engine is associated with this command queue and the next command to execute is a kernel. Now we need to look at what hardware component can execute a kernel. So in GPUs, there are some units called shader engines, and each shader engine has a shader processor input, which is a component that works between the asynchronous compute engine and the compute unit. The compute unit are the cores of the GPUs, and the instructions are executed in the compute unit. Typically, a GPU has a lot of compute unit. Many blocks can be executed at the same time. The work of the kernel launching process is to move the kernel from the command queue to the compute unit for execution. So in the first step, the ACE needs to break down the kernel into blocks and send it to SPI. Then the SPI needs to further break down the blocks into wavefronts and dispatch those wavefronts to the compute unit. So here you may see this word shader again and again. So I want to explain it a little bit. A shader is typically both a software concept and hardware concept. It definitely comes from the word of graphics rendering. A shader basically means you assign the color to something. So you may write a shader program that is typically a kernel that is responsible for calculating some colors. And compute units are sometimes also called shaders, where it's the hardware that can execute a program to determine the color of some pixels. In general purpose computing world, we typically do not need to calculate colors and we do not need to consider those blocks or compute units as shaders. We may more want to call it thread blocks or just GPU cores. And the terminology shader is still there, even if we only care about general purpose computing. So next, let's look at a kernel. A kernel can be broken down into workgroups. And the workgroups can be even further broken down into wavefronts. And we need to map the wavefront to the compute unit. So the whole process is a non-deterministic process, and the driver and the GPU hardware can determine which wavefront goes to which compute unit. And it's actually also non-deterministic in terms of every kernel launch. If you launch the same kernel again and again, you may not have the same wavefront mapped to the same compute unit. But there are still some rules that we can follow. So the first rule is that wavefront from the same workgroup needs to go to the same CU, because we want some wavefront within the same workgroup to communicate using shared memory or using barriers. And the compute unit must have enough resources to hold all the wavefronts within the workgroups. The resources include basically three parts. The first one is wavefront slot. We'll talk about wavefront slot later. And we also consider scalar and vector registers if there are enough registers to execute the workgroup. And finally, we care about shared memory or local data share in AMD terminology if there is enough space to hold the LDS requirement for each workgroup. So let's look at the wavefront, registers, and the LDS. What are those things? In each compute unit, we have some concept called wavefront pools. In each wavefront pool, we have 10 wavefront slots. So each wavefront slot can handle one wavefront. What is the hardware for a wavefront slot? It is basically the resources that keep track of the status of the execution of one wavefront. We may have one hardware register for execution mask, a PC register, and a VCC register, SCC register, and also instruction buffer. It's just the resources to keep track of the execution of one wavefront. Wavefront from one workgroup may be located in different pools, and the capacity of compute unit determines that in each compute unit, there can be at most 40 wavefronts. And this number is different from GPU to GPU, but most high-end GPUs have 10 slots per pool. Then we need to look at the registers. So we have vector registers, we also have scalar registers. There are 4 vector register files and 1 scalar register files. Each vector register file is associated with one wavefront pool. So, for example, if we have one wavefront that wants to go to one wavefront pool, we may allocate some vector register spaces for that wavefront. And we may also allocate some scalar register spaces for that wavefront. Before one compute unit can execute one word group, the compute unit must check if there's enough space in the vector register file and the scalar register file to handle the word group. Then finally, we have LDS. It's basically the same idea as scalar register, and the allocation is dynamic. Every time a word group is launched to this compute unit, part of the LDS is allocated for that word group. So we may do some basic calculation. Let's see how many wavefronts that we can execute at the same time. Assuming we have a M1 GPU, it has 120 compute unit, 4 wavefront pools per compute unit, and 10 slots per wavefront pool. That means we can run 4,800 wavefronts at the same time. Let's consider the vector add example again. Assume we have 1 million data points. That's not a lot of data. Then we may need 1 million threads to execute. Considering that 64 threads forms a wavefront, there are 16K wavefronts in each vector add kernel. So we may see a big gap here. One M1 GPU can only execute 4,800 wavefront, and that is a pretty large number for a GPU, because M100 is almost the highest end GPU that you can buy nowadays. But each kernel, it's a very simple example, has 16 wavefronts. If we have even larger data, we may have even more wavefronts. So how we can deal with this problem? So we have to say that wavefronts cannot be executed at the same time, and we have to take a round let the wavefront to be executed. So we have to introduce a wavefront and a block scheduling mechanism. So remember, in CPUs, when we deal with a large number of threads, but a relatively small number of cores, we can either finish one thread, then start another thread, or we can keep swiping in and out threads. But if you consider GPUs, the state of one block actually contains a lot of information. We have a large number of vector registers and scalar registers, and also local data share status are associated with one wavefront or block execution. Swiping in and out blocks are not likely to be practical. So GPUs typically use this finishing one block before starting another one, these type of mechanisms. That means not all the blocks are actually being executed on the GPU at the same time. So some blocks may be executing at the beginning, then these blocks need to finish execution, then other blocks can start execution. That means global synchronization or synchronization across blocks is generally not possible for GPUs. So far we have introduced how these blocks are being dispatched to the compute unit. In the next video, we're going to dive into the structure of a compute unit and see how instructions are being executed in the compute unit.